Um, Hi, good evening. Am I audible? Great. Hi. Sorry again for yesterday's fiasco. Random stuff happened. Hopefully, my internet will not bonk out today again. So the agenda for today is basically uh, uh, we have around 3 DP optimizations. So 2 are pretty common. One is CHT, Convex Hull Trick, and the second is divide and conquer. We might get to Knuths if we have time. We'll see. But the third one, 1D, I think is slightly less common. Again, it's pretty well known. But that is slightly, I think, not as many people know it as CHT or divide and conquer. So what I'll do is I'll start out with 1D, even though it's slightly more non-trivial than the other two. I'll start out with 1D, so that people who are interested in knowing that can first look at it, and then many of you probably know CHT and divide and conquer, so you can leave after 1D. So that's the plan as it is for today. Okay, so we'll start out with 1D. Will you be showing how to prove divide and conquer? So I'm not planning on going into the algebraic proofs using the quadrangular inequality. I don't think we'll be going into that, if that is what you're asking. We'll give more of just a practical overview of how those work. Okay. So cool. Let me share my screen. Are you going to cover the intuition behind CHT? I hope so. Yeah, as much intuition as I possibly can. Okay. Is my screen visible? I hope my screen is visible, and I hope you can see what I'm writing here. It's hard for me to read the chat though. Okay, you can see. Great. Okay, so I should probably start off by saying that the DP optimizations there are a ton of very good resources available online. The one single kind of holy grail is this blog on CF, A219, called DP optimizations. This has, so again, like CHTs, divide and conquer, Knuth, and 1D is kind of mentioned here, though slightly different, but it's pretty much the same thing. And the 1D I'll be covering is from this blog post by UBC programming team. Though over the last, I think, 1 or 2 years, they've revamped their website, and this page is very messed up. So I'll maybe after sometime over the week, maybe I'll try to make a doc of this and also send it, because it's a very nice document and it's just very messed up. And I tried contacting them and asking them to fix it, but they've not been able to get to it so far. So this is hopefully one thing which we'll do properly. Okay, so coming to 1D, right? So what is the setting? Okay, so just to be clear, so right now I can't see your chats. I don't think there is a way for me to get past that currently. Yeah, okay, so that's just a disclaimer. I can't see your chats right now. Maybe once in some 10-15 minutes I'll come and look if there are any particular questions. So it'll be kind of a monologue right now. So 1D optimization. The setting is the usual typical DP setting, which is, say, DP of I is max or min over j in 1 to I minus 1 of dpj plus some cost function or weight function of j plus 1 to I. Yeah, this is one of the most common. So DP of I depends on something before it. Like usually it's like partitioning array into subarrays, or even things like LIS, lots of things, right? So dpj plus some, from j plus 1 to I, some cost function based on that. This is the one. And what we want is, we want this to satisfy, we want the cost function to satisfy something called the quadrangle inequality. Okay. So what is this quadrangle inequality? The way it's usually given is in this format. Yeah. So for all ij, their w is what I've written as cost. W of ij plus w of I plus 1 j plus 1 is less equal w of I plus 1 j plus w of ij plus 1. But the way I like to look at it is just slightly rearranging it. I think that gives me a slightly better intuition. So which is cost of I comma j plus 1 minus cost of I comma j, and you compare this with cost of starting from one element later, which is I plus 1 comma j plus 1 minus cost of I plus 1 comma j, and we want this to be greater than or equal to. So what does this mean? So this is basically, I have I j plus 1 and ij, right? So I have cost of ij, and when I increment the endpoint from j to j plus 1, what is the differential increase in the cost, right? So that is the LHS, the incremental increase in the cost when I'm increasing my endpoint by 1. And I'm doing the exact same thing, but now instead of starting from I, I'm starting with a slightly smaller. The starting point is, instead of I, it's I plus 1, right? So I plus 1 to j and I plus 1 to j plus 1. What is this incremental increase? This incremental increase should be larger if the starting array is, starting range is larger. I to j plus 1 is larger than I plus 1 to j plus 1, right? So if I start out with a larger kind of like a super range, I comma j plus 1 is a super range. It kind of contains I plus 1 to j plus 1, right? So if I start from a larger range and increase it, then the increase in the cost is greater than the incremental increase in the cost when I started with a smaller thing, right? So this is what quadrangle inequality usually refers to, and you can see that these two. So this is basically just I'm just taking ij plus 1 and ij I'm taking it this side, and I plus 1j I'm taking it this side. So ij plus 1 minus ij plus 1 minus ij should be greater than or equal to I plus 1j plus 1 minus I plus 1j. Yeah. So this is the intuition I usually think of for quadrangle inequality, and this is something which you'll see quite often. And what does this give us? So what this gives us is a nice, so if the cost function satisfies this, then we get this nice property that the place where I break, the optimal place where I break for a dp is kind of monotonic. Okay, so let me kind of clarify exactly what I'm saying. So we have the dp function is dp of I is max over this function dpj plus cost of I plus 1j. So whichever j gives me the maximum dp value, right? So it's like I have dpi. So let's go to the context. Let's just assume we are kind of breaking down arrays into subarrays, right? Partitioning them into subarrays. So it's like I have 1 to I. Where do I want to break it to get the last subarray? And so I get dpj plus cost of j plus 1i, right? So where is this cutting point? And there will be multiple cutting points which give me the maximum. DPI doesn't care about it because DPI is just a value, right? But what we are looking now is the place, the index where I need to cut, okay? And if there are multiple such things, I'm going to take the smallest one, right? The smallest index where if I cut, I get the optimal DP, okay? So think of this as like when you do backtracking in DP, and to find the actual instance, you will keep track of this, right? So where exactly was that argument? So it's like argmax in this case, right? So that let's define by k of I. Okay, so k of I is the minimum j such that dpj plus cost of j plus 1 comma I is equal to dp of I, right? So find dp of I. dp of I is loop over all j's by call dpj plus cost of j plus 1 I, and now which was the smallest j which gave me this maximum value, right? So that we denote by k of I. Okay, and now the nice property that I talked about is k of I is less than or equal to k of j for all I less than or equal to j. Okay, in other words, when I have dp of I, the first place where I can cut to get my optimal, if it's here, then if I'm considering dp of some larger number, larger array, then the place where I have to cut will move to the right. It will not move to the left, right? And this is a pretty natural constraint which you'll see in a lot of situations. So what you'll typically practically end up doing is you'll not worry about these quadrangle inequality and try to prove this. Instead, you'll just kind of intuitively try to see if this equation holds, this inequality holds. This is because this is the final inequality which we want. Quadrangle inequality implies this, but this is what we'll be using in 1D, right? So many times just try some small examples and see if it works, and if it works, it probably is true, right? So now let's assume this. So assume that k of I less equal k of j for all ij. Now how does this help us? Maybe I should just look at chat once. Shivam, quadrangle inequality is just it's a constraint or a condition on the cost function, which if it's at, we are talking only about those DPs for which this quadrangle inequality holds good. Otherwise, we can't apply 1D. It is just a condition for which has to be satisfied for us to do any of this. Sort of related length of interval. Yes, Samar, that's correct. I mean, if the length of the interval is larger, then yeah, that's where the thing comes into picture. Yeah, split screen might work. True. I'm just lazy to fix that properly. Okay, so k of I. So let's for now assume this, right? So k of I less equal k of j for all I less equal j, and this very directly implies a naive optimization, which will end up being pretty useless, but let's look at that optimization nonetheless. So that optimization is basically when I'm computing dp of, say I'm computing dp of 1, then dp of 2, and so on. Say I've computed till dp of I, right? So when I computed dp of I, assume I went through everything from 0, 1 to I minus 1 for j and found the maximum value of dp of I, right? And when I found that, I would have found k of x, right? So basically I'll know where I have to cut so as to get the maximum. Now when I want to come to dp of I plus 1, yeah, the point is I don't need to start my j for this dp of I plus 1 all the way from 1. Instead I can just start it from k of x, right? Because I know k of I plus 1 is greater or equal k of I, right? Okay, maybe I should not write k of x, I should write k of I, sorry. Yeah. So if for dp of I, cutting at 5 was the best option, then for dp of I plus 1, cutting at 4 or 3 or 2 or 1 is not going to work, because we know that we need to cut only later, right? So I can start my loop, my j loop, not from 1 but rather from k of I, right? So my j, I can reduce it from 1 to I minus 1. This is the, sorry, not I minus 1, in this case it will be 1 to I. This was the original thing, but I don't need this. Instead, I'll just go for j runs from k of I to I. Yeah. I hope this makes sense to everyone. Okay. This is a very, it's pretty natural, right? I mean, I hope this is, there's nothing very deep about it. I mean, we're just using this given constraint and just blindly utilizing that advantage that we have, the information that we have. But this is not going to help us in the worst case. Do you see why? Do you see why this is not going to be an asymptotic optimization? And it's the difference you'll see as we get to it. Exactly, Vatsal, you're absolutely right. If Aryan and Vatsal, precisely. Just assume k of, let's say there is a DP problem where k of I equal to 1 for all I. Yeah, this could very well happen. And if this is the case, then your for loop is not changing at all. I mean, it's just k of I is 1, right, for all. So it's literally the same. Your complexity remains exactly the same. I mean, like literal number of executions still remains exactly the same. So this doesn't help us at all. I hope this is clear to everyone. Yeah, cool. But then why are we discussing this? And the point is, we can, even though this kind of like naive approach doesn't work, still this k of I and this is helpful in a different manner, which is what 1D does. Okay. And the way to get to that is to kind of change our perspective of the way we look at this. Okay. So till now we were looking at dp of 1, dp of 2, dp of I, and then we were thinking, okay, I know k of I, so I know k of I plus 1 is greater equal k of I, so I'll go to that, right? So given I was looking at what k of I can be. But now instead we're going to ask the kind of like a reverse question and say, given an element x, rather given an index x, for what all indices I can x be k of I, right? It's kind of a convoluted question, I think. So all I'm saying is, I mean, it's like the inverse of this, right? We had k of x is minimum of j such that this, we are just now looking at the inverse of this. That is, for what values of I will a particular j be the optimal place to cut it? Okay, it's literally just the inverse question we are asking. So why is this perspective nice? So let's go back and see what this says. So this says that k of I less equal k of j for all I less equal j. So assume I found everything, assume I'm at the end of my algo, then consider the array k, right? So consider this, I have this array k where I'm storing k of I for all I, right? So for k of 1 will be which is the place I should cut to get the maximum dp1. It's probably 0 or 1, right? Maybe it's 1. For dp of 2, maybe also it's 1. Right? Maybe for dp of 3, maybe it's 2. For dp of 4, maybe it's 2 again, right? Maybe for dp of 4, it's 3. Now for dp of 5, can I cut it 2? Can the minimum be 2? No, right? Because that is precisely what our condition says. These k of I less equal k of j literally means this array is going to be monotonically increasing. So I'm going to get 1, 1, 1, 2, 3. I'll not get a 2 here. I can only get a 3 or a 4. I might get 3. And then maybe I'll jump to 5. Maybe I'll jump to 7. Okay, probably 7 doesn't even exist. But yeah, something like this. 6. 6. Right. So this k array at the end is going to look like this. Right. It's going to be a monotonically increasing array. Now you should realize that this k array is not something we have. This is something we have to find, because if we had this k array, then the DP becomes trivial from O of n squared. Okay, so before that, okay, a very trivial point which I didn't forgot to make. We kind of we assume that this cost function we get in order one time. I mean, of course, in some problems it might not be order one. Maybe even pre-computation doesn't work. But for this analysis, let's say it's order one, and if it's not order one, the complexity will just increase and the optimization will still work, but that extra overhead will be there, right? Just to be clear, so this DP obviously can be solved in order n square. I hope that's obvious to everyone. I mean, it's a literal order n square DP, right? So coming back here, so if we had this k array, is it clear that we already get an order n solution? Because for every DP of I don't need to go do this loop. Instead, I'll just go to that particular j, which is k of I, and just compute dp of k of I plus cost of k of I plus 1 comma j comma I, and I'll be done in constant time. I can find every dp of I in constant time if I have the k array. So of course this k array is like a secret array which we don't know, and our job right now is to kind of build this k array in a sense. So this k array is what we'll be working with, and we'll be building it kind of implicitly step by step. Okay, I hope it's clear till now. Samarth, I don't see where k of I will always be 1. No, I definitely k of I will. Oh, you're asking for a example. I'm just saying that could be a possibility. I mean, I don't know, like a problem where, say, you want to divide subarray into an array into subarrays, and somehow the cost function, or rather the given elements are such that you want only, like, the best optimal is to not divide at all, like the entire array is the answer, right? So for every I, cutting at the first is kind of like taking the entire array, right? Or maybe cutting at the end. You could consider it as cutting at the first also at some points. So in which case it will again end up being n square. Yeah. No, Snigdha, no, it's k of I less equal k of j if I less equal j is what we are looking at. Samarth, yeah, it is true that k of I is 1 is a trivial case. I'm just it's kind of like the reason I said that was like kind of like a worst case analysis. So you given an array, you don't know that k of I is 1 for all I. You could have an input such that k of I becomes 1 for all I, in which case the worst case complexity, the time complexity for it is going to end up being n square. That was the point. I'm not saying, I mean, if you beforehand know that k of I equal to 1 for all I, then of course you can do it in much faster time. Is there a 1D approach without quadrangular inequality? I don't think so. I think quadrangular, not, at least not as far as I know. I mean, what we call 1D relies on quadrangular inequality, or at least that's my definition. That's my understanding. Yeah. Okay. So coming back, so we have this. So this k array is what we are going to be working with. So let's start from the beginning. So when I'm computing dp of 1, some trivial base case, and at this point we are basically going to consider an array. We are not going to have this array, just imagine this array as having all ones. Okay, basically saying any of these numbers. So we basically have almost no information on when I'm doing my base cases. I don't have any information on the others, right? So yes, this might be the final solution, but for now I don't know which of these are 2s, which of these are 3s, which of these are 5s. So we're kind of saying all of these are greater equal 1. So think of these as lower bounds on the numbers, on the ki values, right? So the lower bounds for all the ki's at the beginning is just 1. Of course, it can't be less than 1, assuming 1 based whatever. So the lower bound for everything is 1, and that is what we fill this array with. Okay. Then let's say we calculate dp of 2, right? So dp of 2 again, let's say it's a base case. We calculate dp of 2, and now what we'll do is we want to see which indices would be better off for which I cutting at 2 is better than cutting at 1. Okay. This is the question we are going to ask. So suppose I'm only allowed to cut at 1 or 2, which is better for which index? Okay. So currently I'm in the first step, think of it as I'm only allowed to cut at 1, right? So they have no option, everyone cuts at 1. Now in the second step, I'm allowing them to cut at 1 or at 2, and then asking, okay, for each DPI, I'm basically going and telling you. So see, basically look at this. For each DP of I, I have I minus 1 options for J, right? What we are basically now doing is we are not at the beginning giving all the I minus 1 options. We are kind of giving it one at a time. Initially, we are giving it only one option. That is, you can only cut at 1. Then I'm saying, okay, you can go and cut at 2 as well, and whichever is maximum, take it. Then in the third step, I'll say, okay, you can cut at 3 as well, and now whichever is maximum, take it. Okay, this is going to be the general protocol. So coming back here, so now after the second step, I'm going to go to all the i's and I'll tell them, okay, now you can cut at 2 as well, and now amongst 1 and 2, which is maximum, you do it and tell me. So once they tell me, I'll go and change this array to say which is better, right? So some of them will still say 1, and some of them will say 2 is better. And now do you see that this is still the monotonicity is going to remain because of this constraint, right? So it will not be 1 1 1 2 1 2 something like this. It will be 1s and then 2s, right? And this is the whole point. And then I'll compute dp of 3. I'll tell how dp of 3 works. And then once I compute dp of 3 in the third step, I again go to all of them and tell them, okay, now you already cut with 1 or 2. Now I'm giving you an extra option of cutting with 3, and now tell me which is the element you prefer. Do you want to stick with what you already cut at, or do you prefer cutting at 3 now? Okay, and then I'll update this array again, and then I'll keep doing this again and again and again. Okay, so this is the overall picture. But now, why are we doing this? So before getting to how we do this, why are we doing this and why does this help us? The reason this helps us is when we are at dp of 3, yeah, before computing dp of 3, I claim that after the first 2 steps, whatever is here, that is k of 3 after the second step, is the actual k of 3. It's not just a lower bound, it's the actual k of 3. And why is that? Because in the first 2 steps, I've given for dp of 3, I've given them both the option 1 and 2, right? And which is exactly all the options it has. dp of 3 has options from 1 to 3 minus 1, which is 2. That's basically, it has options 1 and 2. And I've given dp of 3 both these options, and I've asked it to find it's whatever it prefers, whatever is the maximum. I've taken it and placed it here. So what is placed here is actually, it's not just a lower bound now, it's the actual k of 3, right? So now dp of 3, I don't need to spend any for loop. I can literally just go and say dp of 3 is nothing but dp of k of 3 plus cost of k of 3 plus 1 comma 3. Yeah. So now this becomes a constant time. I can compute dp of 3 in constant time. So kind of generalizing, after the first I minus 1 steps, I can compute dp of I in constant time, because I'll just do dp of I is dp of k of I plus cost of k of I plus 1 comma I. And why does this work? This again works because dp of I has been given all the I minus 1 choices in the first I minus 1 steps to find the best k of I. And so after the first I minus 1 steps, okay, so maybe I should write it down. After first I minus 1 steps, k of I is actually k of I. K of I is exact and no longer just a lower bound. So initially we said these arrays we're considering a lower bounds, right? But now the claim is after I minus 1 steps, k of I is the exact value. I hope this is clear to everyone. No, Divya, I think 8th standard this is probably not for class 8 students. Okay. So I hope this makes sense. So now, given this, now it's obvious why we want to do this, why we want to maintain these things, because it just makes, instead of spending order I time to calculate dp of I, I'm just spending it in order 1 time, which is obviously a huge boost. So now we focus more on how exactly to do what I said. Doing what I said naively is going to take order n time each time, because if I go in everyone and give them one extra option at each step, in the ith step, what is it that I want to do? Ideally, what I want to do is I want to go to each of the i's and tell them, okay, now we have this extra option of cutting at I and tell me which is better. So I have to do a max amongst two DP terms, and that's just going to be order n each time, and then n times that root, it's still going to remain order n square. So that's no use for me. So the point is, how do I do it better? And that is to, obviously, as you would have guessed, to utilize the monotonicity of this k of x. So I know that from 1 1 1 1 1 it is going to shift to something like 1 1 1 1 2 2 2 2 2, right? So this point of changing from 1 to 2, I'll binary search, right? So initially it's all ones. Now I want to find the place where these ones end and the twos start. So I'm just going to binary search for that. This is an obvious place, right? I mean, I'll binary search over x and ask for every x, if 2 is better than cutting at 2 is better than cutting at 1, then my x has to be my actual interchange, the mid. Let's what do I want to call this? Let's call it the transition point, transition from 1 to 2, right? So if cutting at 2 is better than cutting at 1, then transition point is lower. If cutting at 1 is better than cutting at 2, then transition point is higher. And then I do this binary search and I'll get the exact transition point. So then I'll do this. And now from something like 1 1 1 2 2 2 2 2, now in the third step, it's going to either become 1 1 1 1, sorry, 1 1 1 2 2 3 3 3, or it could become 1 1 3 3 3 3 3 3. Yeah, this 2 could completely disappear as well, but it's going to be only one, or it could be all threes. Of course, that's also an option, but it's going to be one of these forms. It can't be 1 1 3 and then 2, right? Again, because of the entire monotonicity principle. So now this is also pretty easy to find, because what am I going to do? I'll just take 3. So I know this was the array, k array after the second step. So when the third step comes, I'll basically go to this 2, this index, the place where the transition point where the first 2 happened, and ask this index whether they prefer 2 or whether they prefer 3. If they prefer 3, then I know everything here prefers 3, right? And then now I'll just go binary search within these ones to find where, or rather I actually won't do that. I'll go ask this one whether they also prefer 3. If they prefer 3, the entire array is 3, right? If not, I have to binary search within these ones to find where the 3 change happens, and I'll get something like this, right? The other option is maybe this index said, no, I actually prefer cutting at 2 rather than cutting at 3. So then it's of this form. So now I have to binary search within these indices to find the transition from 2 to 3, which again is just ordered log n. And I'll get, after the third step, my k array will be something like this, right? Again, just a point of caution, we actually won't be storing this array, because storing an explicit array, because that's going to just updating it is going to be order n, which is useless. But for now, like bear with me. Let's just think of it as an array and then we'll just change it. It's a trivial change at the end. So I hope this makes sense, right? So for the fourth step, suppose after the third step, if I have 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, now after this I'll compute dp of 4 in constant time, and now I have to go change this. And how do I change this? I'll first go take this guy and ask this guy, do you prefer cutting at 3 or cutting at 4? Also note here that to ask this question, to get an answer to this question, I need dp of 4, right? Because cutting at 4 requires dp of 4, which is why it all kind of comes together very well, right? I find dp of 4, and then using this, I can find I can answer my question. So I go ask this index, do you prefer cutting at 3 or do you want to shift to 4? If it says I want to shift to 4, then great. All these guys are now changed to 4s. Then I'll go ask this index and ask, do you want to remain cutting at 2 or do you want to update to 4? Maybe it'll say I want to remain at 2. Then I know that after the fourth step, it's going to be 1, 1, 1, some 2s and then all 4s. So I need to find this transition point, and for that I'll binary search within the 2s and find the place where they transition from 2 to 4, which is again order log n. Okay. I hope till now this makes sense. Yeah, okay. I think all your questions will be answered in the next step that we are going to do. But now, actually, how exactly do we maintain this? Of course, we don't want to maintain an actual explicit array. What we do is we just maintain these transition points, right? So I'll basically have I'll have the endpoints of every, so something like this, the initial array. I'll probably represent it as 1, 4, which means the first 4 elements are all 1s. Then I have 2s which are up till the 8th point. Then I have 3s up till the 11th index, right? Something like this. I'll maintain this. I'll not maintain the actual array. I'll just maintain the subsegments which have all equal values. So this is all I'll be having. And now, do you see that updating it is amortized constant time, or rather amortized log n, because there's a binary search for that. So basically, so it should kind of feel similar to your for every I find the nearest element to my left which is greater than me, the usual stack amortized problem. It has very similar flavor to it, right? Because when a new element comes, it'll pop out 3 if this question said I prefer 4 over 3, then entire 3 is popped out. Then I'll come ask the starting point, which is the 5th index for 2, and ask, do I prefer 2 or 4? If it says this will be popped out, then I come here and I'll do a binary search and I'll insert this, right? So every step I am inserting one segment and removing some number of segments, right? But every segment is added once, removed and removed at most once, and addition of everything might involve will almost always involve a binary search. That's one extra log n, and everything else is amortized constant time, right? So this entire process will end up taking n log n. I kind of went through this very fast. I hope this was clear. So I hope, Samarth, that answers your question. Worst case, yes, it will be, each step will be order n if you ask for each transition point. But then amortized, it becomes total n log n because of this addition removal each point. But you have to check every segment if it will change. So what if there are n segments? Exactly, Vatsal. If there are n segments, then you will not have to check every segment. You'll have to keep checking until you hit a point where you don't remove it. So those segments which you checked, whatever segments you checked are removed and will never enter back again. So that's like that's an amortization cost function. You assign if you want to actually do the amortization, you'll assign a weight of 1 to that. I hope all of you know amortization. If you don't know amortization, this will be kind of complicated, but if you know amortization, this should hopefully be clear enough. Is it more like a stack? Yes, it is exactly a stack. You could think of this as 1,4 is the bottom and 3,11 is the top. And when 4 comes, it will first check with 3,11 and maybe it will pop it out. Then it will come to 2. It might pop it out and then stay, or it might stay at the very top. But you'll have to change this 11 to something else based on what the binary search tells you. Yeah. If the 3, I mean, if it's 3, 3, 4, then it should be changed to 3, 10 and then 4, 11. Yeah. Querying at the first portion, just an extra optimization. We could always just binary search over the entire array. Divyansh, I hope your question is resolved. No? You can't just binary search over the entire array. You have to binary search every segment. You have to only binary search that segment where you know you have to. If you keep binary searching every segment, then that could be like as someone said, that could be like order n segments, and each step you'll end up doing n log n, which is bad. So the whole complexity in the worst case will be n log n into cost function. That's correct. Yes. Yes. Why not use a difference array? What exactly do you mean, Nischay? Difference array for what? I'm not quite sure what you mean. Updates in order 1 for k of I. Oh, you mean actually keeping the array? I think I get what you're saying. It's going to be pretty similar to this, right? I think the end result is, if I understand what you're saying, I think it's I'm sure there are different approaches to this as well, but then you can't get over the binary search at every step. That should be done. It's not that trivial. You might have to go back and overlap on previous k of I. Yeah, exactly. That binary search is something which you can't get over. I'm pretty sure of that. Any implementation has to have that binary search. So you can't get rid of that log n, at least in this approach. So coming back, so that mostly solves the entire problem. So now what you'll be doing is you'll be having this stack. So there's just kind of okay, maybe I should move this somewhere else. Yeah. So summarizing what we learned, what we discussed so far, we have dp of I. We have this one particular format of dp of I is dp of j plus max over dp of j plus cost of j plus 1 to I. This is the only type of dp function we are seeing. And over this, we have this extra condition that it should satisfy either the quadrangle inequality, which you almost never sit and work it out. Instead, you just intuitively see whether k of I is less equal k of j for I less equal j. If that is the case, then you try and find every dp one by one, but when you find it, at every step you keep track of the lower bounds on each k of I, and this you maintain using a stack. And after the first I minus 1 steps, whatever lower bound you have for k of I will be actually k of I, so you can find dpi in constant time. And now that you found dp of I, you can go and give the option of cutting at I to everyone, but you don't give it to everyone. Instead, you go to the start of every segment and give that option only to them. If they prefer the new option, you throw away the entire segment. And at some point, one segment will say, no, I prefer sticking with the old one. And so inside that, you'll have to binary search and find a place where they prefer going to the ith, cutting at ith. So now your stack will kind of reduce, and you'll put in 1 at the top. And now your ith step is done. Now that ith step is done, dp of I plus 1 can now be computed in constant time using k of I plus 1, because now that is an exact value, not just a lower bound. And that just goes through. Yes, Arsh, we'll look at an example. Yeah. Cool. So now coming to an example problem. So okay, so just to be clear, so everything I said till now is from this very weird page right now, but believe me, like if you jumble the equations here, you'll get almost exactly what I said. I mean, see, this is one. Everything is I've just literally plagiarized from this. There's nothing new I said. Yeah. So yeah, that's basically it. So now we'll come to some examples. Let's actually start with the second example, which is a USACO problem called acquire. So this is a pretty nice problem. So let's just, I hope my screen is visible and the font is not too small or anything. So let's just go over this problem, and let me just check. Yeah. So what is this problem? So you're considering, you're a farmer who's considering buying some land for the farm, and you have n rectangular plots that you would like to buy, and each plot is of course in integer dimensions and some wi cross hi, wi cross li. So now there's this interesting cost function, which is that you want to buy. So basically, okay, so maybe I should give the link of these things. Okay, I should have actually done that earlier. Let me paste these links. And this last link is the problem that we are looking at right now. So maybe go over it once. Okay, spend like a couple of minutes reading it once, and then I'll start discussing it. And in the meantime, if there's any doubt, feel free to ask. Yes, definitely. I'll share these on Discord. Yeah. Second link was this. What do you mean it's not visible? I mean, when you open it, it doesn't, as in the page doesn't load, or the link it doesn't show in the chat. Okay, that is very weird. None of the links show up, or only the second one? Second link. Okay, maybe it's to do with some length. Let me try breaking it up into two. Do you see now? Aruj, yes, definitely. CHT is possible. So a lot of these DP optimization, not a lot of these, a lot of problems, CHT and 1D are kind of interchangeable. Okay, the second portion doesn't show. Okay, let me just give it on Discord then. let me give. Yeah, I've sent it on Discord, on the Discord channel. Cool. So going back, yeah. So I hope you read the. Okay, so yeah, you got the link only now. So read the problem once. Yeah, so Arjun, as I was saying, yes, sorry, Aruj, a lot of CHT and 1D problems are kind of indigenous because as you can see, the DP model is exactly the same, right? It's pretty much, you don't have, if the cost function is like some function of I into a function of j, then you get exactly y equal to mx plus c, right? If this no, sorry, if you have this into a multiple plus this, then you get that. So yeah, so it can definitely be done with CHT as well. You're right. Okay. forget what I said. I definitely messed it up. I'm just saying. So the problem that we'll be discussing now, I'll tell you. So when we solve it, it'll be pretty obvious to people who know CHT that can be done with CHT as well. Cool. So let's go over this problem once. I think I know what the problem is. Yeah. So let me start here. Acquire, right? So what you have is you have n different plots which are w1 into h1. I'll just go with height. I don't like length. w2 into h2, wn into hn. You want to buy every single of these plots. It's not like you want to choose, but rather what you will do is you'll kind of partition this set. It's not a subsequence, it's a set, so you can reorder it. Ordering is not important. You will partition it into sets, into subsets, and each subset you'll buy, right? And what is the cost of a subset? The cost of a subset is the largest width into the largest height in that subset. Cost of say S is a subset of these, then the cost of S is max wi in S into max hi or rather I in S. Yeah, amongst yeah. So this is the cost of a subset, and you have multiple subsets, and you add up all of this, and you want to minimize the total cost. I hope the problem is clear. Yeah, cool. So now how do you go about solving this? So it's a nice problem in that there is a couple of initial observations that you need to do, which is probably obvious to a lot of you who've seen something like this, but it's still nice. Which is, so the first pretty natural observation is that if I have a plot like this of some 10 cross 7, and I have another which is say 8 cross 4, that is 8 is less equal 10 and 4 is less equal 7, then whichever subset I'm choosing 10 cross 7 in, I'll choose 8 cross 4 in the same subset, and my cost is not going to increase, right? Because this is max and this is max, so the actual cost, this is not going to change by including this 4 comma 8, or sorry, 8 comma 4 in that set. So in a sense, this is irrelevant, right? I can just ignore this rectangle and then at the end I'll just put this rectangle in whichever subset 10,7 goes into, and my answer will remain exactly the same, right? So I'm removing a rectangle and my cost remains exactly the same. So this is what we call a irrelevant rectangle. So okay, I should find out a shortcut to do this, but for now bear with me. Yeah. So in particular, if Wi is less than or equal to Wj and Hi is less than or equal to Hj, then I is an irrelevant rectangle. Yeah, so I'll just remove the ith rectangle and my solution doesn't change. So let's assume we've done this. So it's not, so first, how do you do this? So this is again something which you probably would have seen in a lot of problems. So one way to do this is just sort everything based on W. So I have W1 less equal W2 less equal W3 less equal Wn. And now look at H1 and H2. If it is not the case that H1 is greater equal H2, if it's the other way, that is if H1 or rather if H1 is strictly greater than H2. If H1 is less equal H2, then W1 comma H1 is irrelevant and I'll throw it away. I'll pop it out. Yeah. So we assume that H1 is greater than H2. Now if H2 is not greater than H3, that is if H2 is less equal H3, then W2, then the second rectangle is useless. So I'll pop it out. Then I'll also check whether H1 is less equal H3 or not. If it is, I'll again pop it out. It's again like the amortized. You can do this in amortized constant. So total order n time. You can clean up this input, and at the end you'll basically get it as this, right? So Wi's are less equal and Hi's are greater equal. One is increasing, the other is decreasing, because if at some point both increase and increase, then the first one can be thrown out. I hope the intuition is pretty clear. Yeah. Not always, Aryan. We'll get to that in a bit. So now we can assume that the input is of this format. W1 is less equal to W2 and H1 is greater than H2 is greater than H3. I think we can just go with H less equal. I mean, I don't think it matters at all. Just looks better. So now we come to the next observation, which is if I am choosing say 10,3 and I don't know 20, oh sorry, one second. And 20, 100. If I'm choosing both of these in the same subset, then is it clear that choosing 15, I don't know, 30 in the same subset doesn't change my cost? It doesn't increase my cost because 15 is less equal to 20. Sorry, I kind of messed up. Okay, this should be decreasing. Sorry. Let's redo this entire thing. So my Wi's are increasing. So let's start with say 2, 100, and say I go to 50, 10. If both of these are in the same subset, then something like 20, 30. Choosing this in the same subset will not increase my cost. Why? I'm going to take max of the heights, max of the widths. So max is 20 and max is 50 and 20 is less equal 50. So this doesn't increase the max width, and 30 is less equal 100, so it doesn't increase the max width as well. So choosing this in the same subset as these two is not going to change my change my cost. So in this order, if I'm basically choosing something here and something here in the same subset, I can as well choose everything in between them in the same subset, and my answer is not going to change, right? This is the continuity, like contiguous. So now we come to a very familiar realm of DP, right? So usually in DP we want contiguous subarrays. Subsequences are pretty hard. Subsets and subsequences are hard, right? We probably need to go to 2-power and usually, right? So we want to get to contiguous, and this is the observation which gets us to contiguous. So what is observation? There exists an optimal solution in which every subset that we choose forms a contiguous segment of this order. And what is the proof? Suppose not, suppose no optimal solution is like that, then take some optimal solution in which there exists at least one subset where there are two rectangles and such that everything inside it is not chosen. Then we exactly use this argument and say, no, I can change it and the answer is not going to change. So I'll get an optimal solution with the condition that I want, the continuity condition that I want, which is a contradiction. So my initial assumption that there is no such optimal solution is wrong, which leads us to the proof that yes, there is always an optimal solution in which this nice continuous property is satisfied. So we are just going to find that optimal solution, right? So now what is the problem? I hope I kind of went fast. I hope it was clear. Right, why can't I move? How can we sort since order is important? Aditya, order is not important. The original problem says nothing about order at all. I can choose whatever I want. I've posted a problem with a different statement. It's the same problem in Discord or something. Oh, okay. Cool. So Aryan Mascara, yes, exactly. So now the problem reduces to partitioning. So the original problem did not have anything about order, but now we've reduced it to a problem where we gave it one particular order, and now the subsets I want are partitioning. And now we see that we come to the familiar DP, right? So now what is going to be the definition of DP of I? DP of I is just take the first I elements, what is the answer? The usual DP definition, and should again be pretty obvious that this is just nothing but the naive DP is just max over J, where J varies from what do I want J to be? I want DP of J plus cost of J plus 1 to I. Cost of J plus 1 to I is going to be nothing but H of I, sorry, H of J plus 1 into width of W of I, right? So this is going to be H of J plus 1 into W of I, and J is going to range from 0 to the last element can be J as well, right? No, J minus 1. Yeah. So I hope this DP equation is clear to everyone. The cost is this because of this particular order. The heights are decreasing. So for any subarray that I'm taking, the cost is going to be the height of the first into the width of the last element, because the max of heights is the first and the max of width is the last. So height of the first into width of the last, and DP of everything before it was just DP of J. And this naively leads us to an order n square solution, which is super trivial. Yeah, it's just directly implementing this without any worries. But now we want to optimize this, and we want to get this to order n log n. And now here, for people familiar with CST, do you see that this is a direct CST application? I mean, y equal to mx plus c, cj, mj, and xi, right? So this is this can be solved directly with CST, and the things are monotonic. Everything it goes through very cleanly. But for people who don't know CST, don't worry, we'll get to that. But now we'll do this using 1D 1D. So why does 1D 1D work? So remember that we basically want k of I to be less than or equal to k of j for all I less than or equal to j, and what you do in a contest is just try this for some small values and see that it works. But the intuition is not that hard. So it's basically, if I have these set, and if I'm breaking here, and now I'm considering more number of elements, more number of rectangles, why will I ever increase my last set, right? That does not make a lot of sense, right? So I'll only, because I'm adding more, I'll only come more towards the end, and I'll be looking at a smaller thing, right? That's the, I'm going in a very hand wavy thing, and this basically just depends on, this is a very problem specific intuition most of the times. In this problem it's pretty clear, but in some problems it will not be obvious. But I think the kind of like the most practical solution is just to check for some values and see if this actually works, because it'll be clear when you need an optimization to the DP that you already have. So this will usually work out. So now if we have this, then the problem becomes pretty easy, right? So now it's exactly following what we did, no change. It fits the exact model, the inequality is satisfied. So we do exactly as it is, and we'll end up with order n log n instead of order n square. Okay. It should be min till, min. Sorry, my bad. Not max. Min until I minus 1. Yeah, not j minus 1. Purchase the land in successive groups is in the problem statement. It's not consecutive groups, but it's, I think by successive groups they mean successive as in like one after the other. It doesn't mean the grouping has to be consecutive. I mean by some group of things, and then by some other group of things, and then by some other group of things. That is what they mean. It doesn't mean that it should be consecutive. Yeah, exactly. So cool. So that is just 1D. So this is one simple inequality, reduces our complexity from order n squared to almost linear n log n, right, which is pretty great. Cool. So now let's should we look at batch scheduling? Okay, let us look at batch scheduling as well. This is a considerably harder problem, but it's still pretty nice. Let me give this link. Yeah. So Samarth, I don't know about CHT being more powerful than 1D. There are definitely problems where you can't use CHT, but I think 1D works. So I don't think it's a superset in a sense. So in this case, the cost function was of this nice format of f of j into g of I, right? Which is why you could make this mx plus c. Plus c is fine. That's always some function of j. That is good. But the cost function, breaking it down into f of j into g of I, doesn't always happen, right? If this happens, then yes, you can always use CHT, right? And write it as mx plus c. But if this doesn't happen, then you can't use CHT, right? But then the 1D condition, the quadrangle inequality might still hold true, in which case you can still use 1D. I hope that makes sense. Vivan, no, I don't think we'll be doing Disha over this time. Now, they are not comparable. I'm pretty sure there are problems. So yeah, I mean, like you have, just because something follows the CHT model does not imply it has to be it has to solve this inequality as well. CSD is kind of a pretty generic thing, right? It's just of this form. It doesn't say anything about the quadrangle inequality or anything of that kind. Yeah. Cool. So let's read batch scheduling, which is, I think, here. Yeah. Keep reading. I'll be back in 1 minute. Yeah, I consider that Samarth. Maybe we actually should. Okay, we'll just finish this problem. Okay, we'll try to. It's a pretty nice problem. Even though it's been a long time since I saw it, I hope I remember it enough. Okay, so let's go over this quickly. There are no other questions, right? Yeah. Okay. So batch scheduling. So you have these. You have n different jobs. Each job has it's an ordered jobs. Each job has a time time ti required to complete it, and it has a cost factor of fi. What you should do is you should again like partition into subarrays, batch them together, and the finishing time for every job in a batch is considered to be the ending time of that batch. So, and the cost for every job is its cost factor into the time at which that batch ends. And the final solution is sum of all this. But then there is also an extra setup time S, right? So each time a batch is started, this extra setup time S is added. It takes time to start a batch. That is there, and the goal is to reduce the total cost. So basically, if S wasn't there, then the obvious thing is to batch every single job on its own, because as you increase the size of a batch, the earlier jobs time increases, right? So that is the one-way pull. So you want to keep the batches as small as possible so that the multiplicative thing remains smaller. But as you keep the size of batches small, the number of batches has to increase. So the number of times S is added increases. So that's the other way pull. And the goal is to kind of figure out how you manage this tug of war. Yeah. So I hope I didn't miss anything else in the problem. I think that's the entire problem. Yeah. Okay. So now let's look at some. I'll probably mess this up, but let me go ahead again. So the trivial, the natural DP. Let's write it down. DP of I is the cost of doing the first I elements, first I jobs, which is going to be right here. Which is the direction we eventually want to go to? Yeah, you'll need to keep track of okay. Yeah, so the issue is you don't know how many times you have to add S, right? That's the main issue which crops up when you try to do the naive DP. So the naive DP itself doesn't work, right? The first thing itself will be hard to figure out. So what we instead do, so I hope the issue is clear. This S depends on the number of times you break down at the beginning. So you don't know what the time is currently. It's not just the sum of the times till now. It's also the number of times S has come. Right? So instead what you do is you account for this S in future jobs. Right. So basically, when I set up a new batch, what I'm basically doing is delaying the ending time of every job after me by an additive term of S. Right. I hope it kind of makes sense. So let's just take one particular job, say the X job, let's say the 10th job. The ending time of this is the ending time of whichever batch it is in, which is nothing but the sum of Ti of everything till here plus how many ever S I've added before me, right? So if I've added 4 batches before me, including this, it's 5th. So it's sum of all the Ti's plus 5S, right? That will be the ending time of this job. And that ending time is going to be multiplied by the cost factor of, which I think is called F, right? So it's going to be multiplied by F10, right? But now what we'll do is, the issue with the DP is we don't know what this 5 is. We don't know 5, right? Because we only keep the DP will only keep the minimum cost. It will not keep track of how many times I've divided. That will require another parameter, and that's going to mess up things unless we do some manipulation. And this nice manipulation is, okay, I have this summation of Ti plus this I'll keep, but this 5s into F10, I'll take it out common. I'll take it out and I'll redistribute this cost in a different sense. So how am I redistributing this? instead of counting this 5s into 10 in the cost of 10, I'm going to add s into F10 in each of these 5 places where I created a batch, new batch. So it's basically redistributed. It's kind of like the amortization thing, and it's kind of like redistributing your costs. The cost is actually incurred by the 10th job, a cost of 5s into 10, 5s into F10, but I'm redistributing it as s into F10 in 5 different places, right? So basically, whenever I'm starting a batch, I'm contributing an additive term of s into fi for every job I which comes after me. Right? I'm increasing the cost contributed by them by this much. So I'll not count it them. I'll instead count it to me. So when I'm creating a batch, I'm basically increasing my. I'll consider the term s into summation fi I ranging from whatever, or let's say fj, j ranging from I to n, where if suppose I'm at the ith place. So this is an extra cost which I'm incurring right now. Okay, and now the usual DP will kind of go through, right? Because this was the main pain point. So now that we have taken care of this, so now when I want to find DP of I, the first I elements, suppose the last batch starts at j, then till then I have, so it's min over j in whatever 0 to I minus 1 or 1 to I minus 1 something of dp j remains as it is, plus now in the cost of j plus 1 to I, right, cost of j plus 1 to I. So the naive cost is the finishing time of all this into the cost factor of all these guys. But then I've split it into 2 such terms. So this term is going to be pretty easy. That's just summation of all the times into summation of all the cost factors, right? So that is just going to be summation tk, k ranging from 1 to I, this into for each element in j plus 1 to I, their cost factor, right? So summation ck, k ranging from j plus 1 to I. Yeah. So that is the easy cost. But now the cost given by s was the hard cost because we didn't know what, but we've rearranged it, and so now I'll consider this cost which I'm adding to everyone in the future, right? Now in this case the future is from j plus 1 to n, right? So I'll be looking at s into summation k ranging from j plus 1 to n, not just j plus 1 to I, j plus 1 to n, cost factor ck. Yeah. So this is my total cost, and now I'll take min over all these guys, and that gives me dp of I, and then the usual dp goes. So this is right now an n square dp. I hope this makes sense. Not clear, is it? So there are 152 confused. Ouch. Okay. Can you maybe again put thumbs up or confused if it's clear or not clear? Before that, let me just make sure that I got the final thing correct. Yeah, looks mostly, yeah, I think that's exactly what I wrote. Yeah, I think that's correct. Okay, so I think most of you have understood it. I did definitely go over it fast. I I'm sorry about that, but it's just it's a nice manipulation. It's a pretty nice manipulation. Basically, the main funda is basically this, right? The cost of one particular job with the times TI is just typical DP. There'll be no confusion. If you just do the math, it's a very simple DP. There's no issue there. But the issue comes in figuring out the S factor, the S term. How many S's do I need to add? And that's not clear because I don't know how many batches I started before. So instead of adding them here, I add them whenever I create a batch. So I'm kind of accounting for future costs whenever I'm creating a batch. And this is like it's not a very rare trick. It's not at least it's not very common to me. But there are definitely some more problems where this rearrangement of costs helps us get rid of this. So that's the main trick here. There's nothing much more. That's basically the main trick I wanted to kind of show by taking this problem. Yeah. And now it's order n squared dp, and now you see that this this satisfies the. We will not go into why this satisfies the quadrangle inequality, but just see that the ki thing. This again is not very hard to see because it's multiplication of things. So the larger you go, it's better to cut smaller, right? It never makes sense to go in which multiplication is just going upper and higher and higher. In this case, actually, the quadrangle inequality is also not very hard to get the intuition behind, because a larger thing, and when you go larger, this extra thing you add will multiply with a lot of things, so the incremental increase is going to be higher than when you take a smaller and increase it, in which case it multiplies only with smaller number of elements, right? So it's actually not. This is something you can actually sit down and do, and also I would recommend that you sit down and intuitively think, and it shouldn't be that hard. Does 1D have a full form? It's just one dimension. So I believe where this comes from is something like your divide and conquer, as we'll see, is kind of, it needs a 2D thing, whereas this is 1D. There is actually something about this which I looked up at some point. I frankly don't remember. Let me look it up and let you know. It's a nice term. It has some actual meaning which I'm not able to think of right now. So the 1D basically refers to the fact that the trivial DP is a 1D DP. I'm not sure what the other thing refers to. I believe I did look this up at some point. I'll try. If I can figure it out, I'll let you know. I'm not exactly sure right now. Yeah. I don't think so, because this I've seen some things being referred to as like 2D 1D and 1D 2D and things like that. It's not something I've seen. It's a very probably the maybe the NOI people, or maybe the Russians, I don't know. Somewhere this is it's probably the Chinese, because I know 1D came from Chinese Olympiad, so it's probably the Chinese who refer this as some IDJD, and they have some significance to that. But I don't think it refers to the KR. It's not that specific. It's a more generic term which they use. I believe this is what it is. I'm not even 90% sure. So don't take it with a pinch of salt. But it's something to do with it, is what I believe. So cool. So that is 1D. Yeah. So we'll stop 1D there. Any questions? I think that's about it, right? Cool. So now we'll move on to the more common stuff, which has a lot more resources written on them. So I'll try to do it pretty fast. I might even just look at. Yeah. So the first is CHT, Convex Hull Trick. So I should probably just start out by giving the links, because there is this amazing blog by Soumik. I think CHT and divide and conquer we'll do. I think that's better. Okay, sure. I'll give all the links on Discord at the end, but for now I'm just giving it here. Yeah. So CHT, right? So coming to CHT, other things. Cool. So CHT is actually a data structure, even though it's called a trick. So the main question is basically, given some number of linear functions and given some queries, at every query you want to find which of those functions evaluates to the maximum or minimum. Okay. So let me write it down. So you have n functions, right? So f of 1, it's linear, so it's some m1x plus c1. Yeah, so if f of this is some other m2x plus c2. Okay, so you're given these are the functions which you have. This could be online, this could be offline. For now, let's assume it's offline. That is, you're given all these functions at the beginning, and then you're given q queries, and each query is a xi, and you have to evaluate f1 of x1, f2 of x2, fn of xn, and output the maximum of this. So the answer for the input query x1 will be max over f1 of x1, comma f2 of x2, dot dot dot, fn of xn. Okay, and you're given many such xi's. You're given x1, x2 up till xq, and the data structure basically has to answer these in logarithmic time. Right, so this is the data structure we'll be looking at. And why is this helpful? This is helpful because, again, this, as we saw in the previous thing, so this form is something which keeps coming up in DP quite often, and there's this nice way to look at how that works. We'll definitely look at some problems, and this is probably the most common DP optimization trick, and it's used in a lot of places. So this is something you should definitely, even if you don't look at 1D CHTs, if you don't know CHT, you should definitely look at CHT and be very comfortable with CHT. So what do we do? How do we do this? So the first step is kind of to start thinking in a geometric sense. So these are all functions, but then of course these are also, you can think of these as equations of line, right? I mean, just because I've written in that form, it's obviously equations of line. So you basically have lots of lines, right? Some random lines which are here, and for every input query xi, you should find which line is at the top, right? In this snapshot, in this vertical, which line is at the top. If I have something else, some other xi, here this is at the top. Actually, this will be at the top, but I mean, you get the point, right? So this is the geometric view which we'll be working with. So why is this helpful? So let's start with one basic observation, which I think is the Advitiya. No, x1 does not remain the same for all functions. Oh, you mean x1? Yeah. When I'm asked the first query, I evaluate every function on the same query point and find the maximum. Then for the second query, I have to evaluate each of them on x2 and find the maximum. Right? Yeah. So in that sense, yes, x1 remains the same for all functions. Cool. So I think the main point behind CHT is this one observation, which is, if I have one function or a line like this, let's call this line L1 and say at this point, at this, let's say x1, I evaluate this line to be the maximum for query x1 if L1 is the maximum, right? Suppose that's the case. Then if I take some other L2, okay, where slope of L1 is greater than slope of L2, right? By slope, it's like, I mean, L1 is this, so L2 is something less steeper, right? Or it might be even negative. If I take such an L2, then the claim is L2 will not be the maximum anywhere in this side. In greater than x1, L2 will never be the maximum. It could be the maximum for something here, because L2 could be something like this, right? In this case, at this point, at this x2, L2 is the maximum. It's larger than L1, right? So L2 could be the maximum amongst all the n lines. But for any xi which is greater than x1, L2 can never be the maximum. Why? Because if I have if at this point, if at this x3, I claim, if at this x3, I claim L2 evaluates more than L1, right? So that means L2 is somewhere here, L1 is here, so L2 is above this, right? And L2 slope is smaller than L1, so it's going to be something like this, right? In which case, even at x1, L2 would be larger. I mean, we can prove this using this thing, but I think intuitively it's very obvious, right? If I have something like this, and I'm looking at a lower thing, here if it's larger, then here also it's going to be larger, right? So if L2 is greater than L1 at x3, then L2 has to be greater than L1 at x1 also, but that's a contradiction because we said L1 was the maximum there. So this can't happen, right? So that's the whole point. So if I have this L1 and L1 is maximum somewhere here, then at some other places it can only be a line whose slope is even larger than me. It can't be a line whose slope is lesser than me. Okay. And one kind of what do you say? Check, like a sanity check. Yeah, sanity check is what I was looking for. One sanity check is that if I have all these functions, right? If I evaluate, if my xi is plus infinity, right? It's a huge number. Then can you blindly tell me which of these functions is going to give me the largest value without actually going and evaluating it? Which function is going to give me the maximum? Yeah. Sure. Yeah. So it's because x is so huge. Do you see that these ci's don't matter at all now? It's just going to be the function with the largest m. Yeah, the largest m, because it's multiplied with plus infinity, is going to be as large as possible. The c don't matter. It's like asymptotic analysis, right? You don't care about the constant value. You really care about what is there, because we care about large values, and here it's the largest value possible. It's plus infinity, so it's the largest slope. So when you look at your graph, when you look at the plane, towards the right, it's going to be the line with the highest slope, right? So it's going to be like this. At the end, it's going to be this one line with the maximum slope. This is going to be the maximum. Every other line is going to be down like this somewhere. Yeah. And similarly, if I put x equal to minus infinity, then of course the function with the smallest m in most cases it's going to be in cases it's going to be like negative, largest negative value, right? So that is going to be like this, right? And this is going to be the maximum in plus infinity. So it starts out, when you come from left to right, it starts out from the lowest slope, then something larger slope, then some other larger slope, then some other larger slope, some other larger, and then you kind of my drawing is super bad, but I hope you get the picture, right? So it's like this, then like this, then like this, then it could come like this. Okay, this is also bad, but yeah, you get the picture, right? It's going to be like this. This is what we call the upper envelope, right? So if we kind of mark the segments where that line is the maximum, right? That entire segment or a ray, I mean the endpoints are end segments are going to be rays, two rays. Those will form like a almost like a paraboloid shape, right? Where it's going to start from lowest slope all the way up till highest slope, and this is called the upper envelope, and he has a very nice picture. Yeah, so there are these lots of things. The bolded things is the upper envelope. He calls it the convex hull. I think a better word is upper envelope. And our answer basically lies only on this. We don't need to care about anything below because the maximum is only amongst this. So the data structure is just going to basically maintain this upper envelope. And similarly, if instead of maximum you want a minimum, you have a corresponding lower envelope. So it's exact opposite. It's going to be like this, right? Yeah. Oh, I'm running out of time very soon. So yeah, so that is basically the main funda, and the question now is basically how do you maintain this? And maintaining this is kind of similar to the convex hull thing you would have seen. So now, because you know that what matters is the slope, you can just sort everything by slope and then keep adding them one by one, and you just have to find out their intersection points. At some point you might end that you have to skip something. So if I have this and then this line, and then a third line which comes like this, then the upper envelope becomes this, right? And the second line is irrelevant, right? And this is pretty similar to I hope what you'd have already seen in your convex hull algo. It's the right turn and then popping one out because it's irrelevant, right? It's the same algo you use here. It's the same trick, the stack, and you pop it out. You see the line of you see the point of intersection, and if it's before this, then you pop this out. The same funda. So I'll not go into the depth. Again, this Meow has done a great job. I think he also has a animation of that. Yeah, he actually has an animation of that as well. So you can just see this animation. It's literally the same thing which you do always, and you can after sorting it by slope. All this I'm talking about in the offline setting. You can sort everything by slope and then keep adding them. Adding them is just going to be constant. It's going to be amortized constant times, total linear. So only the log n to sort is going to be the bottleneck. And once you have this entire thing, basically what you'll have is every segment you have the endpoints. You have the endpoints and the x coordinates of the endpoints, and each segment you maintain which line it came from. And now when a query comes, you just binary search on this, find which segment your thing lies in, and just evaluate that function. Do you know which function is there in that? You just evaluate. You take that function and evaluate xi on that, and you give the answer. So pre-processing is like order n log n because of sorting, and then each query is order log n. So this is the kind of the simplest thing. And then what happens when you have to? It's not offline; it's kind of online. In a lot of problems, what you'll end up having is that the lines, each function, by online, what do I mean? You have updates you have insertion of lines or insertion of new functions. And this usually happens most commonly that the slopes actually end up being the new function which comes, its slope will actually be larger than the previous slopes till now. And that is typically because, I mean, in your DP, it will be like dp of I is kind of the slope, and dp of I is usually greater or equal dp of I minus 1, something along these lines. And so your slope will be large, it will keep increasing. So you only have to, the online and offline almost have no difference, right? I mean, it's just like offline, you keep, it's just that you have to interleave it with queries. It's going to be the same. But then there is also the better approach, I mean, a more general approach where you don't have this constraint, where the lines can come wherever they want, right? So you maintain this envelope, but then now you get a new line which need not be at the end, it could be anywhere. And this again is not very hard, you just binary search and find the place where it has to go, right? And then you check to the left and right which all segments it has to pop out. This itself might be irrelevant, in which case you don't make any change, again based on the same intersection points. Or you do you'll have to keep something like a set, and you keep popping out its right neighbors and keep popping out its left neighbors, and you maintain the new set again, right? And yeah, that's usually what happens. One small save you can do sometimes is that the queries also will be monotonic. That is, xi is greater or equal xi minus 1. And in that case, and if it's not this fully dynamic version, but it's you add only at the end, then the queries can actually be done in amortized constant and not log n, because you can keep like a pointer and throw the lines out as and when you're done with them. So it's kind of like a 2-pointer approach in a sense. The sets are like this, you keep adding lines this side and the queries come out, and each time a query goes beyond a segment, you throw the segment because you know you're never going to use it again, right? So it's you don't need to do a binary search, instead you do a linear search, which becomes order log n, right? So but then it's just a log n factor, so it almost never matters. Yeah, sure. I mean, all this is, so I personally, because I'm biased because I didn't learn from you. I learned from this Brian B's tutorial. Where is it? I didn't write it here. WCAPG. Yeah, this one. So this I think is a brilliant article, which does everything I've said so far. Again, nothing I've said is new. Okay, I don't know why it's so WCIPG has this bad habit of sometimes going offline, so it'll be good if you just save these locally, or it's at least this is there on WebArchive, but this UBC is not there in WebArchive also, which is bad. So this covers literally everything I've said. Okay. Now I think data structure wise there is implementation. I mean, they just look up. I mean, the links I gave have implementations. I didn't get the case where we need to pop from the left in case of online setting. Can you give me an example? You never pop from the left. You only pop from the right. When you're adding here, you pop from the right. Do you mean in online setting, in the fully dynamic setting? So in the fully dynamic setting, sure, I'll draw an example and show. Say the upper envelope at some point is this, and the new segment you add, say it's like something like this. Okay. So this segment's slope is between this segment and this segment. The slope is between this and this. Say, my drawing is not perfect, but you can see that it could be like that. right? So you want to insert it here, but then you see that it makes this segment irrelevant because of the intersection point. It intersects this before it intersects this. So it has to pop this segment out from the left, right? So the this is kind of inserted between these two, and it also pops out the guy to its left. That is, I hope that makes it clear. Yeah. And in this case, it doesn't have to pop anything from the right, but if this was somewhere here, it will also have to pop from the right, or it might have to pop out multiple things from the left and right. Which DS? Just use a set. I think set is what people usually just use. Cool. Okay. So then coming to the main thing, which is how is this used in DP problems, right? And let's take the same example of which we did before, which is acquire. Yeah. So as we saw already, acquire has this DP. Yeah. So this was the acquire was the problem where we had many rectangles and a cost for a subset is the max width into max height, and you want to minimize the cost. And we did this, we remove all the rectangles which are not needed, and then we sorted them, and we got WIs are increasing and HIs are decreasing, or the other way around. Yeah, same. Yeah, WIs are increasing and HIs are decreasing. And then we had this other argument that there is an optimal solution in which you take only consecutive rectangles. And then the DP was pretty clear. So this is the DP. Let me just write it down clearly at the end. DP of I is min over j from 0 or 1, I don't know, to I minus 1 of DP of j plus the widths were increasing, heights were decreasing. So height of j plus 1 into width of I. Yeah. So this was the DP equation, right? And now, why do we say this is CHDable, right? How do we make this into a CHD problem? So the point here is, when I'm computing DP of I, what I want is minimum over some j things, right? But this is not, it's not obvious how this is mx y equal to mx plus c. So what we'll be considering, the functions we'll be considering are basically this. f1 of x is h2x plus dp of 1. f2 of x is h3x plus dp of 2, and so on and so forth. So fi, let's not say fi, fj of x is hj plus 1x plus dp j. Okay, and now do you see that this function is basically this? This is nothing but fj of wi, because it's hj plus 1 into x plus dpj, right? It's mx plus c, where m is hj plus 1 and c is dpj, and I'm evaluating it at wi. And importantly, this wi remains same across all j's, right? wi is independent of j. It depends only on I, right? So dp of I is nothing but take all these, you'll take till I minus 1, take all these I minus 1 functions, evaluate all of them at wi and tell me the minimum value. And that is literally what dp of I is. And now you see, this is exactly the CHD model. You have I minus 1 linear functions, and you want to find and you want to evaluate, and you have queries where every query is find the minimum of all the evaluations. We did maximum, minimum is also exactly literally the same. There's no difference. Yeah, and that's basically CHD. And so again, so let's sorry. Yeah, so basically here my slope is hj plus 1 and my c is dp of j, right? So, and as we saw here, our h's are, or in this case it's decreasing, but I could have taken the exact opposite and it'll also work. If it's decreasing, okay, I mean it's the same thing except I have to do it in the other way around, right? It doesn't change anything. I should have actually probably done the other way around. That would have made life easier. But it's the same. It's monotonic, and that's what mainly matters, right? So I'll be adding lines. We looked at adding lines on the right. This will be adding lines on the left, but nothing changes. Yeah, and you evaluate the wy, and wy also, as you see, is monotonic. So this doesn't need binary search. You can actually do a linear search and get away with it. But still, you have to do at the very beginning. You have to clean the input. You have to do order n log n. So that will be the bottleneck. If that was given to you sorted, then I think, yeah, I think after that everything can be done in linear time. That doesn't have to be any log n, because you don't need a set. Instead of a set, you can just keep a vector, because a stack or a vector. Because you are guaranteed that the slope additions are monotonic, so it's only at the end. You don't need any binary search and doing stuff. And the queries are also monotonic, so you can just keep a pointer and not have to do a binary search. But I mean, you can just feel free and just do normal CHD, and you'll not TLE. The log n will usually not matter at all. dp of j is constant, hj plus 1 is slope, that's correct, and wi is the x value where we want to query. That's perfectly right, Arjun. Yeah. Should be extended by at least 10 minutes. Cool. So that is, so this is how it will usually end up being. So you will have dp of I is min or max over things before me, and you have this term, and the point is to massage this dp equation in such a way that it becomes some function of j into some function of I plus a function of j, right? So what we'll want is dp of I is min or max of j, something from say 0 to I minus 1, and this entire function you want it to be some function j some function I shouldn't call it a function. Let's just say it's a constant function which depends on j, right? So it's like mj, right? And into this x can be a function of I, right? So it's again x I plus cj, right? This is what you want to massage it to. And if you have it in this form, and you see here, this is just this is mj, this is xi, and this is cj, right? And if you have it in this form, then all these guys are linear functions. So each of these you think of it as you think of it as linear lines, and you take them in or max using CHD, and that's about it. There's no quadrangular inequality, nothing. It's all pretty clean. It's just this, you need this particular DP equation model format, or model to work out. And it will be nice if these MJs are MJs are monotonic. It will be nice if the Xi's are monotonic, but it doesn't have to be. You can work with general MJ and general Xi as well. It's just a bit more pain. Okay. So again, for CHD, I would very highly recommend looking at this this blog. So there is acquire is discussed, and then there is, I think, 2 more problems. Yeah. So commando is also a very nice problem. So CHD, the kind of the hard part lies in massaging the inner DP term into this format. So similar to what we did in batch scheduling, it wasn't obvious at the beginning, so we had to massage it to get it to that format. That's pretty much what happens here as well. Yeah. This fully dynamic is what we meant by like insert in the middle. So you can do deletions, I believe. I've never read it fully, but using some, I think, persistent treeps or something, you can do it, I think. Yeah, there's a lot of blogs. Maybe not a lot of blogs, or at least some blogs on this. If you're interested, you can look at it. If you're also interested, you can look at a problem called Killer. Yeah. So this is a problem which does CHD, but using quadratic equations, not linear equations, quadratic equations. So I think it's a pretty nice. You can have a look at it. It's Tangent Malvika's problem, which is pretty nice. Again, but not very generic. It's a very. If you just want a challenge, you can have a look at it. So cool. So that's CHD. Can I spend some 10 more minutes and walk you through divide and conquer very quickly? Yeah, I'll definitely give resources. I mean, like, the resources are literally everything is there in that one blog post, but these extra things which I have also, I'll give them. Cool. Okay, so I'll just try to speed run divide and conquer. So divide and conquer, again, there is this one, I think this is the problem which most people use. So it's called Seal and Gondolas. Have a look at it. So I hope you've read the problem. Let me go over it quickly from, yeah, it's just summation of sum of levels of okay, Uij is given. Yeah, okay. Yeah, so so the input to this problem is a 2D matrix. It's given to you. Where Uij represents the unfamiliarity. It's like the cost between a pair of people, and you basically have these n people in a row. Order is important. What you want to do is you want to batch them up into at most k, I believe k, right? Yeah, there will be k. Oh no, it has to be exactly k, not at most k. It has to be exactly k, because I think yeah, qi should be positive. Yeah, so you should have exactly k batches or k gondolas or k subarrays, where each subarray is non-empty, right? And the cost of one subarray is all the, if there are, I don't know, m elements in that, all the MC2 pairs, you take their uij and add them up. So it's basically some cost function. We don't care too much about the cost function. It's a cost function for a subarray, and you need to minimize the total sum. And this, of course, leads to the very natural DP. DP ij is the first I people. If you are making them putting them into j gondolas, what is the minimum cost you can have? And this is going to be nothing but min of okay, let's maybe let's say g gondolas, right? So it's min of j ranging from 1 to I minus 1 dp j g minus 1 plus cost of j plus 1 I. Yeah. Basically, the last gondola you're saying is from j plus 1 to I. So then dp j g minus 1 plus cost of this, and you want the min over all of these guys. Pretty easy, nothing very hard. So this is going to be what is going to be the complexity. The number of DP states is n into k, and you spend n times, so it's order n square k is the naive DP. Space complexity is n into k. Yeah. What we'll want to do is we'll want to reduce this to, I think, n log n k or nk log n. Sorry, or n square log k. One of those two. One of these we'll change it to k. I don't remember which. We'll get to that. Yeah. So that's the optimization we're looking at. And here, so like in 1D we had we wanted ki less equal kj. That was the condition we eventually wanted. Here the condition we'll want is basically not dp. So like that we had k. Here also let's define. Okay, I shouldn't use the k again. Let's say opt. I think opt is what they use in the editorial of this. So opt of ig is basically the place where is the min j such that this term is equal to dpij, right? The first place where you can break, right? So it's arg min of this entire thing. Yeah, this is opt ig, okay. And the observation is basically that opt ig is less equal opt I plus 1 g. What do we mean? So we have the same number of gondolas, but I have more people. I claim that in the last gondola, the people I sit is not going to be more than, so this is extra person. More than that, I'm not going to add more people. Yes. So if there were I people, say the last gondola had these many people. Now there is an extra I plus 1th person. Yeah. So if there are G gondolas and I people, the last gondola had these many from I to no, not from I, from opt of IG to I, right? This was the last gondola. Now an I plus 1th person has been added. Fine. Maybe this guy I'll put into the last gondola. That's also fine. But what I won't do is go add more people from the past. I'll not take people from the previous gondola and add it here and claim this is better for my from my I plus 1 people, right? And this is pretty intuitive, right? Because the opt the cost function for a single gondola is every pair, right? So when I'm adding a new person, it's already adding more. So the larger a gondola, it's again the quadrangular inequality kind of comes into picture, right? I mean, a larger the larger the guy, the incremental increase is going to be more, right? So if I already have this, I'm already going large, so now incremental is going to be more than what was there earlier. So I wouldn't do that. That doesn't make sense, right? So this again, I'm not going to the algebra part, but this is what we eventually come to. If the number of people increases and the gondolas remains the same, I'm not going to go take people from the previous gondola for my last gondola. Okay, this is the main. Let's see. Yeah. Oops. Okay, and how do we utilize this? Again, as we did in 1D, the naive optimization would be when I'm computing dp I plus 1g, I don't start my j from 1. Instead, I started from opt of ig. This is an optimization, but it's not going to be asymptotic, because again the same thing, because instead of, if every opt is at 1, it's still going to be n square k. There's not going to be any difference, right? But the nice part here is consider your dp table. Yeah. Say this is, I usually take n cross k, but here we take k cross n, right? So dp ig would be ith column and jth row. Yeah, it's slightly different from our usual convention. At least my usual convention is the opposite. But let's go with this for now, right? Ith column and jth row is my dp ig. Now, when I'm filling this dp, I'm going to fill this row wise, right? And that's why we took this protocol, not the other way around. I'll find all dp1. So I'll find dp I1 for all I. Then I'll find dp I2 for all I. And I'll find dp I3 for all I, and so on. And it's obvious that doesn't matter, right? Because ig depends on j is smaller and g is also smaller. So either direction works. So this is the direction we are going to go with. We are going to go row wise in this. So now when I want to compute the gth row, all these guys have already been computed. But I'm not going to start from the left. Instead, what I'm going to do is I'm going to first find dp n by 2 g. That is, I'm going to find this middle element. Okay, I should probably start a new thing. So this is my table. This is k cross n, and I am right now at the gth row. Yeah. So I have to compute dp ig for all g. The obvious thing would have been to start from dp1g, then dp2g, then dp3g, and use the monoton and use that thing to keep my j start from opt of I minus 1g instead of 1. But we saw it's not asymptotically better. So instead, what we go is this nice divide and conquer business, which is I first find dp n by 2g. Okay, and how do I find this? This I do brute force. By brute force I mean the naive dp, right? I run my j from 1 to n by 2 minus 1, and I find the answer for this. And when I find the answer for this, I also find opt of n by 2g, right? So this I find, this is going to take n time, order of n time, and I find opt of n by 2 g is found. And so now this element has been filled. Okay. Now the next thing I'm going to find is I'm going to find dp n by 4 g dp 3n by 4 g. And now what do I know about opt of n by 4 g? I know it's less equal opt of n by 2 g. So my for loop now, my j for loop inside this can run from 1 to opt of n by 2 g. It doesn't have to go all the way up till n by 4. It has to go only up till this. And I know that opt of 3n by 4 g is greater equal opt of n by 2 g, right? Because again, what was the thing? Opt of something larger is greater equal opt of something smaller, right? So opt of 3n by 4 is greater equal opt of n by 2. So I can run my for loop from opt of n by 2g to n. So now this and this combined, the for loop runs for n time, right? This runs from 1 to opt of n by 2g. This runs from n by opt of n by 2g to n. So this plus this, whatever it is, I don't know what it is because I don't know what opt of n. I'm doing like analysis also side by side, right? So I don't know what it is, but wherever it is, it's this plus this. This sum is going to be n. So this both of these guys. So I'll compute this and this. I compute, and the sum time taken to do that is n, right? And then now it's pretty clear. It's like the usual divide and conquer business. So then I'll go and find dp n by 8 and what is this? 3n by 8 and 5n by 8 and 7n by 8. And opt for the j loop for this needs to only run from 1 to opt of n by again, when I found dp n by 4 8, I also found opt of n by 4 8. Similarly here also I found opt, right? So whenever I'm computing dp, I'm also storing their opts. So to compute dp n by 8, my j loop only needs to run from 1 to opt of n by 4 g. And for 3n by 8, it needs to run from opt of n by 4 to opt of 3n by 4. From opt of n by 4 to opt of n by 2. Yeah. And for 5n by 8, it needs to run from opt of n by 2 to opt of 3n by 4. And for 7 by 8, it needs to run from opt of 3n by 4 to n. Right? So this entire, all these 4 dp's together, it takes only n time. Right? And I would have computed all this. And of course, now it's obvious that the number of levels in this is going to be log n. Right? So in each level, I spend n time. And I do this k times. So it's k into n into log n. Yeah, and that's about it. So from k n square, we've reduced it to k n log n, and this is divide and conquer dp. Is this related to observations we used in 1D only? The opt array satisfies the. Yes, that's right. Knuth is also again like very similar. I'll share some link for that. It's also like very similar. I mean, it's usually in like you have two things and it's in between, and Knuth is probably the least used optimization. I think I only know like literally only 2 problems which use Knuths, and one is like a very artificial problem. It's super rare to. I think it's probably the least used optimization, but it's not hard. It's again very simple. I'll give some link for that. And again, the math behind all these things, the actual algebra is time consuming. It's not hard. There is a non-trivial effort you need to put into it, but you almost never do it. You just kind of assume it and do it. And once you leave that part, it's all usually the same things. There's nothing very hard about it. Yeah. So let's stop here. I'm already 20 minutes out of time. So I'll share all these links. In particular, let me just reiterate. Kind of the gold mine is this one blog. For CHT, I would recommend both WCAPEG and Meows. So maybe you could look at Meows first and then you could look at the WCAPEG, because I don't think Meow covers some of the generalized versions, or not. Okay, he does, but I vaguely remember it not being very but he of course has a lot more problems, and then I think the comment section also has a lot more problems. So for problems, you should definitely look at this blog. But I would also suggest looking at Brian's article. For 1D, it's this one weird page which I'll try to kind of fix and send at some point, maybe in a week. I'm not guaranteeing. I'll get to this at some point. Yeah, this has been in my to-do list for a long time. That's 1D, and divide and conquer. It's this. I actually don't know a good resource for this. I'm sure it's there. I'll search and send. But I mean, the resource is just this, and the tutorial of this has the solution. There's nothing much deeper about this. Yeah, and Knuth is there in like random Quora and some random blog posts, which I also had sent links to. Oh, okay. I didn't know CPL go ahead, divide and conquer. Okay, cool. Great. Okay. Thanks. Bye. Any questions? I think that's about it, right? So let's stop here. See you.